There is a problem with the kilogram. The kilogram is the last basic unit of the international system of units to be defined by a man-made object. This is a platinum-iridium alloy that is kept in Paris. Careful measurements of the international prototype kilogram compared with the identical standards around the world have shown that the masses are in fact diverging. This is approximately 50 micrograms over a century. Having this divergence is unacceptable when it comes to improved measurements accuracy. In the same way as the meter was redefined using the speed of light, which is a fundamental constant, the kilogram can be defined by the fundamental constant called Planck constant. To see how it works, consider this. We first take the existing definition of the kilogram, which is the cylinder, then we measure as carefully as possible how it relates to the physical constant. Then we set this exact value of the constant and use it to redefine the kilogram. Since the Planck constant can be written in terms of the kilogram, a link can be made between the macroscopic and microscopic words.
This can be done using the wet balance. It operates on two mechanisms. On the left side, the weight of the alloy cylinder is compared with the force on a coil subjected to magnetic field. Here B is the magnetic field, L the length of the coil, and I the current through the coil. M is the mass, and G the gravitational field. Since the two plates tend to an equilibrium state, the mechanical and electrical forces are equal. On the right side, there is a motor which tends to push back and forward the coil with a constant velocity. This motion induces a voltage which is proportional to the coil velocity, where V is the voltage, B the magnetic field, L the length of the coil, and V is the velocity. Rearranging these equations, we get the electrical power equals to the mechanical power. So, how do we go from power to Planck's constant? There is actually a way of measuring the voltage accurately using a macroscopic quantum effect that involves Josephson junctions. It consists of two superconductors separated by a thin insulator. When electromagnetic radiation is applied to the junction, a potential difference is created across the device. So we have the voltage which is equal to the Planck's constant frequency over 2E, where E is the charge. For n junctions, we have n times h, which is the Planck's constant F over 2E. These junctions are put into the circuit with the coil, and the voltage induced in the coil is balanced using these junctions.
How do we measure the current? The current can be written as V over R, where V is the voltage and R the resistance. The current is passed through a resistor and V is measured using the Josephson junctions, where V equals N times HF over 2E. To measure the resistance, we use another macroscopic quantum effect called the quantum Hall effect. But first, the general Hall effect is observed when a magnetic field is applied perpendicularly to the current passing through a probe. The Lorentz force then pushes the charge carriers to the edges of the probe until the electric force created by the additional charges cancels the magnetic force. The voltage between the edges is called the Hall voltage. This voltage depends on the resistivity of the material. In a similar manner, the quantum Hall effect is observed in a two-dimensional system. When this system is subjected to a very low temperature and a strong magnetic field, the resistivity as a function of magnetic field is quantized. As far as it is known, the plateaus do not depend on the particular structure of the device, its material, the size, etc. This effect is explained by the fact that the energy levels of electrons and its number of degeneracy that is proportional to the magnetic field put restrictions on the resistivity. So we get the resistance to be 1 over P times H over E squared. The Planck constant, therefore, is defined rather than measured. This fixes the value of the kilogram in terms of the second and the meter and eliminates the need for the international prototype kilogram. After 20th May 2019, it will be redefined in terms of this fundamental physical constant.